everyone. I am Sujani, faculty in physics at Institute of Aeronautical Engineering. Today we are going to discuss about physical significance of a wave function. To understand the wave function, you need to look at the introduction to quantum physics, de Broglie hypothesis, wave particle duality, Davison and Germer experiment, and the time-independent Schrodinger wave equation. All these topics I have covered in the previous lectures, which you can refer to understand the physical significance of wave function. So whenever I talk about a wave function, you need the background regarding how the quantum physics has developed and what was the radical hypothesis. So to understand a wave function, you need to understand the de Broglie hypothesis and also about the wave particle duality of radiation as well as matter, and then the Davison-Germer experiment which proves the wave nature of electrons, and we need an equation to represent the matter waves and how Schrodinger has derived the equation to represent these waveforms. That also we have seen in our previous lectures. So today we will see the physical significance of wave function. Now, how we go about this topic? First, we will start from something known to unknown, because when I talk about a wave function, so it may be a new term for you. So whatever you know, what we have studied in classical mechanics, we will start from there and then we will try to understand the physical significance. So we will go from a known thing to an unknown thing. Then we will derive the differential equation or represent, and then the solutions of these differential equations are giving us the wave function. That is how we are going to understand the wave function. Now, according to de Broglie, I told you need to start from here, because he started with the wave nature of particles. So if light can act like a wave sometimes and particle at other times, then matter, usually thought of particles, should exhibit wave-like behavior. That is why we are talking about matter waves. Otherwise, matter always was considered to be as particles. So because of this hypothesis given by de Broglie, now we are considering the electrons to be exhibiting wave-like behavior. Now, what he said is, since radiation has been shown to possess dual nature, because radiation is showing both the natures, wave as well as particle. So matter also must possess dual nature. So how we are expressing this dual nature? Radiation is supplemented with particle characteristics. See, radiation, which is a wave, is supplemented with particle characteristics to explain some phenomena like photoelectric effect, which we have discussed in detail in the previous lectures. And on similar lines, material particles have to be supplemented with wave aspect to understand their behavior. This is what de Broglie proposed. Now, we have seen the time-independent Schrodinger wave equation. At the beginning of 20th century, there was experimental evidence to show the wave-like nature. I told you about this Davison-Germer experiment and others who could prove the wave-like nature of atomic particles. So there is an experimental evidence also in the 20th century. So electrons were able to give diffraction phenomena. So the bending of the electrons, when they are allowed to pass through double slit, they gave diffraction patterns. This helped to understand the wave-like nature. So, in order to understand this, we need to assume that there should be a wave equation to explain these atomic particles. So, we had the wave equation. Now, if there is a wave that is associated with particle, now we are talking that a particle exhibits wave nature. Means a wave is associated with a particle. Then there must be a function to represent it. How do you represent that particle as a wave? So you need a function, and that function is known as wave function. So hope you understood what we are trying to see in this lecture is regarding wave function. So you need to understand what this wave function is. First of all, we started with matter, which exists in the form of particles. Then de Broglie said it should also exhibit wave nature. So when we are attributing a wave nature to a particle, then there should be a function to express that wave. So we are using this wave function. So wave function is defined as a quantity whose variations make up matter waves. When this wave function varies, you can plot and show a matter wave. It is represented by the Greek symbol psi. This is a Greek symbol. P is silent here, so we say it as psi. Psi is the Greek symbol. And this wave function consists of two parts. One is the real and the other is imaginary part. So how are you representing this wave function psi is equal to A plus IB. A here is the real part and B is the imaginary part. Okay, so here it is a complex number. You have a real part also, you have a imaginary part also. So to understand the wave function, we will take an example from classical mechanics. I told you we'll be going from known to unknown because you know Newton's laws which are used in classical mechanics. So first we will try to understand how equations are framed and how do they help us. If you understand that, you can apply the same thing to wave function also. Now, we are considering here a spring. This is a spring. Okay. This spring is attached. One end of it is attached to a rigid support. This is a rigid support means which will not move. This is a rigid support. And the other end is attached to a mass M. Okay. You have a spring of mass M and it is fixed to a rigid support. Now, if I just displace this mass which is attached to the spring and leave, so it may move back and forth. And if this spring is an ideal spring, it will obey Hooke's law. What is Hooke's law? The force that is applied is directly proportional to the displacement and opposite in direction. So more the force you apply to pull this, more the displacement. That is the concept which you know. That is what Hooke's law says. The force is directly proportional to the displacement and is always opposite in direction. So what we write, if you replace this with a constant k, because it is in opposite direction, you write it as minus kx. So this is what we get from Hooke's law. F is equal to minus kx. Now what does the Newton's second law tells us? F is equal to ma. M is the mass, A is the acceleration. So here you have F is equal to minus kx and according to Newton's law we have F is equal to ma. Since the left hand side is the same, we can equate the right hand side. So what we can write here is ma is equal to minus kx. So what is acceleration? Acceleration is nothing but rate of change of velocity, dv by dt. And velocity is nothing but change in rate of change of displacement. So I write it as d by dt of dx by dt. Velocity is given by dx by dt. So A is equal to d square x by dt square. This is how you have to understand how we are writing the equations. We started with Hooke's law and then we are comparing it with the Newton's second law and substituting for A, d square x by dt square. So what will our equation be now? M into d square x by dt square is equal to minus kx. On substituting for the value of a, you get m into d square x by dt square is equal to minus kx. I can bring the kx onto the other side, we will get plus kx. So we have got a differential equation. This is a second order differential equation. Now once you have a second order differential equation, you can solve this equation and get the value of x. Are you able to understand how I am trying to relate? What we are going to do now is, whenever you have an equation, how did we get the equation? We are trying to observe the motion of this mass which is attached to the spring. What are the laws it obeys and what is the equation we get. So we have got the equation m into d square x by dt square plus kx is equal to 0. So on solving this, what you get? X value. So x is equal to a cos omega t plus phi. So what is x? X is nothing but displacement. So now it is the other way. We have derived the equation, but what I want to tell you is, if at all you have an equation, on solving the equation, you can get the displacement. If you get the displacement, you can find the velocity also, because v is equal to dx by dt. You can take the derivative of this. How do you get the derivative? D by dt of x. So we'll write d by dt of a cos omega t plus phi. So derivative with respect to t. So I have, for cos it is minus sign, and for omega t it is omega. So I'll have minus a omega sine omega t plus phi. Once we get the velocity, you can find the acceleration also. Acceleration is nothing but dv by dt. You can write it as d square x by dt square. So we will now take the derivative of velocity. What did we get for velocity? Minus a omega sine omega t plus phi. What will it be? So minus a is a constant, a omega. So for sine omega t plus phi, we get cos omega t plus phi, and for omega t we get omega. So minus a omega square cos omega t plus phi. So what I want to tell here is, if you have an equation which describes its motion, you can find the displacement, the velocity, acceleration, and also momentum, kinetic energy. How do you get the momentum? Momentum is nothing but mass into velocity. You know the mass, you know the velocity, you can directly get the momentum. So kinetic energy. Kinetic energy is given by half mv square. So you know the mass, you know the velocity, you can calculate the kinetic energy. So we are starting with the equation. We are trying to extract various parameters from that particular equation. Now, Schrodinger equation plays the same role in quantum mechanics that was played by Newton's second law in classical mechanics. So that is what you need to understand the wave function or the Schrodinger equation very clearly. What it says here is, the Schrodinger equation is playing the same role as Newton's second law in classical mechanics. So we get the wave function by solving the second order differential equation. There we were getting the position of the particle. Here we get the wave function. If you take the Schrodinger wave equation and you solve it, you will get the wave function. That is why Schrodinger wave equation is the fundamental equation in quantum mechanics. This is a very fundamental equation. So if you have to understand quantum mechanics, so you need to first understand the Schrodinger wave equation. Now in classical mechanics, we can define the exact position of the particle. Why? Because when I am talking about particle, it is localized in space, you can tell about its position. But in quantum mechanics, what we are talking about we are saying it may have wave nature. So we may not be able to tell its exact position along with the momentum. Also, if you see the example of an electron which is revolving around the nucleus, because in the atom, if you have the nucleus and the electron which is revolving around the nucleus, at a particular point of time, how do you locate its position? Okay. Also, you consider it as having the wave nature here. So it is difficult for an electron revolving around the nucleus. We cannot solve the problem using classical mechanics. Means you cannot find the momentum also, because it's moving with the velocity. You cannot pinpoint its position. So position and momentum cannot be described simultaneously. So what approach we use here is the quantum mechanical approach. So we are going to use the quantum mechanical approach even for electrons, or to find the energy, the momentum or the position of the electron in an atom. Now in quantum mechanics, if you are using the quantum mechanical approach, how do we describe the particle? So we describe it in the form of a waves, which we call it as wave packet. And every wave is always associated with a quantity which varies with time and space. So whenever I am talking about a quantity, I am representing it by a group of waves. So it will vary with position, it will vary with time. So the wave function psi is an essential element in quantum mechanics. So when I am talking about a wave function psi, it is a function of both position and time. It varies. Now we can get any meaningful information about the system using psi. So if you know psi, you can talk about other information also that we are going to discuss now. So if you are talking in one dimension, 1D here means one dimension. In one dimension, for all one-dimensional problems where we consider it in a one-dimensional plane, we talk only in terms of x-coordinate and time. How does it vary? But if you have to talk in three-dimensional, where we are talking about the movement of electron in an atom, we have to consider the three dimensions. So in three dimensions, psi will be a function of r and t, where r is for all the three coordinates x, y and z. Now, wave function is a complex quantity and it is not an observable quantity. I've told you how we are representing it. So, it is a complex quantity. It has a real part as well as a imaginary part. But when a wave function is multiplied by a complex conjugate, how do you make this complex quantity into an observable quantity? As such, wave function is not an observable quantity because it's a complex quantity. But unless you observe it, certain things are not clear. You cannot find the parameters. So how do you make it as an observable quantity? So what we are doing here, we are going to multiply it with the complex conjugate so that it gives us a real quantity which will have a definite significance. Are you able to understand? So henceforth, whenever we are talking about a wave function, we may not talk only in terms of psi. We will talk about it in terms of psi star. So let us understand what this psi star is. Psi is given by a plus ib, a the real part and this is the imaginary part. Now I want to write the complex conjugate of the psi and I will denote it by psi star. So psi star will be a minus ib. So you must have learnt it in your basic mathematics. How to write this I is replaced by minus I because I square is equal to minus I. So now psi is equal to a plus ib. Psi star is equal to a minus ib. Now I want psi star. So we will try to multiply these two equations. This is psi. This is psi star. So I want to get psi into psi star. I want to multiply psi with psi star. So a plus ib into a minus ib. This is of the form a plus b into a minus b is equal to, what do you have? For a plus b into a minus b, is equal to a square mathematical expressions formula. A square man. So here I will write it as psi star is equal to a square minus I square b square. IB, no, IB we have minus IB into IB we have I square b square. So the formula is a square minus b square. So now we know I square is equal to minus 1. So when I substitute for I square minus 1, I get a square plus b square. So everything is real here. So psi star is equal to a square plus b square, which is a real quantity. When it is a real quantity, it is an observable quantity. So then it will have a definite significance. That is why we are always trying to multiply this function with its complex conjugate. Now, what is the physical significance of this psi? Let us try to understand the points one by one. The wave function psi has no direct physical meaning. It is a complex quantity representing the variation of matter wave. So we have already seen in our lectures, whenever we have to represent the particle in classical mechanics, you can represent it as a particle which is moving like this. But when we see it in quantum mechanics, it may be a wave function which is moving. So then what happens here is, it is a complex conjugate quantity which is representing the variation of a matter wave. And also this wave function, it connects the particle nature and wave nature. When we are talking about a wave function, we are talking about a particle which is exhibiting wave nature. So statistically we can connect both of them. Now psi square or psi star psi. Okay. So if the function is complex, we know that psi is complex here. So always we take psi star psi or simply psi square. Psi square or psi star psi. Psi square here also means that we are multiplying psi with its complex conjugate. And it is at a point is proportional to the probability of finding the particle. No, if you are taking only psi, because it's a complex quantity, you cannot observe it. But when you take psi square, it gives us the probability of finding the particle. What is the probability of finding it at this position? What is the probability of finding the particle at this position? And so on. So the probability of finding the particle at that point at any given time can be obtained. So the probability density at any point is always represented by psi square. So what psi square represents is the probability density. Now, if the particle is present in a volume, dx, dy, dz, means I'm talking about 3 dimensions here. Then how do you write it? As psi square dx, dy, dz is equal to 1. So when I'm talking about psi square is talking about the probability of finding the wave function. I'm talking about in a particular volume. So suppose I'm considering a cube. The particle is located inside the box. So I denote these 3 characteristics. Okay. So when I have to describe that, then I will take psi square with respect to dx, dy and dz. And the probability, psi square is always giving us the probability. What is the probability of finding it inside the box is 1. So when it is definite, when I am talking about the atom is here or the particle is here, it has to be inside the box. So the particle, the probability is 1. So psi square dx, dy, dz is equal to 1. And now, if I cannot pinpoint the coordinates or I cannot talk about the region where the particle exactly lies, it is somewhere in space, we say, then how do we extend this condition, or how do we find the wave function? Integral minus infinity to infinity psi square dx, dy, dz. So when you are talking about integration, it is nothing but a continuous summation. Integration is nothing but continuous summation. So what you want to find is the particle is somewhere in space. You do not know the limits exact. So suppose if I want to find it in the particle, if I know the length, breadth and height, so I can put the limits, and somewhere here inside the box, the particle, the probability has to be 1. But here in this case, if it is in space, then I will apply the limits from minus infinity to infinity. So minus infinity to infinity is psi square dx dy dz is equal to 1. Psi square can also be written as or psi star psi. No, we have clearly understood now why we are taking psi star psi, because psi is a complex number. We are multiplying it with its complex conjugate so that it becomes an observable quantity. So the wave function that satisfies the above condition is said to be normalized. So we can say this is the condition for normalization. So what is the normalization condition? So you also should know what is the normalization condition. The normalization condition is integral of psi square dx dy dz should be equal to 1. If it is in the space, we consider it from minus infinity to infinity. So this is the normalization condition. Now what are the characteristics or the limitations of this wave function? Wave function psi must always be finite, and it should be continuous and single valued. So when I am talking about a particle which is in a box like this, okay, so it should be, if the particle is here, it should be finite. It should be continuous. When I'm talking about the wave function psi, it should be continuous. Okay, and it should have a single value. Now the first derivative of the function must also be finite, continuous and single valued. If psi is finite, when I'm taking the derivative of it, which gives me the other parameters, then it also should be single valued. Then the wave function psi vanishes at boundaries. Means if I am telling that this particle is inside this box, whose dimensions are L is the width, I say 0 and L. Okay, the wave function is finite inside, it is continuous, it is single value. But when the wave function comes here, outside it cannot be. The wave function cannot be outside. So at the boundaries, what will happen is the wave function vanishes. And also we have seen that the wave function must be normalizable, means psi square must be equal to 1, means the probability of finding it inside the box should be equal to 1. That is the maximum probability we know. Okay, so all these are characteristics. You should remember psi must be finite, continuous and single valued. Then the first derivative of it also must be finite, continuous and single valued. And if the particle exists inside this and we give the boundaries to it, so at the boundaries it should vanish and it should also be normalized. Now what is a Born approximation? Okay, so in the year 1926, Max Born, this is the name of the scientist, he gave the statistical interpretation for psi square, because I told you the statistical interpretation connects the particle nature and wave nature of the particle. So according to him, the probability of finding the particle is proportional to psi square or psi star. Now, what do you understand by this value of psi or psi square? We will not talk now in terms of psi, we talk in terms of psi square. So what is the physical significance? What do you understand? A large value of psi square means a strong possibility of finding the particle at that point. So when you can find the value of psi square gives the probability of finding the particle at that point. And the large value of psi square denotes what? The strong possibility of finding the particle at that point. So this is how Max Born has given the statistical interpretation for psi square. Now, when I talk about probability, it is not fixed. It will change with time. If I'm talking about a wave, Okay, at different time intervals 0, t by 4, t by 2, 3t by 4 and t. So at different intervals, this is the wave. So what will be the probability of finding it at this time will not be the same at this time. So it keeps on changing with time. But Braun's interpretation gives us an idea of how to extract meaningful information about the particle's position and also from the Schrodinger equation. We have solved or we have derived a mathematical expression, okay, for the wave to represent it, and we are calling it as a Schrodinger wave equation. Now, in other words, how do I put it is, the position of the particle can be extracted from psi of x, which is given by Born's approximation. So, this helps us in extracting the position of the particle. Now, the probability per unit length of finding the particle at position x at any time is given by P is equal to psi star xt, psi star psi. Psi here we are taking as a function of x and t, position as well as time in one dimension. Now, what is the probability of finding it in a length dx? If you have to find the probability of finding it in a length dx in this region, so you will take psi star psi dx. Now, I don't want to find in a small region dx. What is the probability of finding it along the x-axis? So, the probability of finding the particle somewhere along the x-axis will be integral of psi star psi dx. You are integrating. Integrating means taking the sum from here to here along the entire x-axis. Now, if the particle exists, it must be somewhere on the x-axis. So, what will be the probability of finding the particle? It should be maximum, it is unity. This we have already discussed. But how do you write the representation I am talking about? So, psi star psi should be equal to 1. No, because the particle, we know for sure that the particle lies somewhere along the x-axis. So, psi star psi of dx should be equal to 1. And this is called the normalization condition. So, a wave function is said to be normalized if it satisfies this condition. Once this condition is satisfied, that is psi square of dx is equal to 1, means the wave function is normalized. Now, when we have to write it in terms of other coordinates also, the square of the function, if you have to put it, what is normalization? The square of the wave function determines the likelihood of finding the particle at a particular position in space. Okay, so which is given by P of y dy will be equal to psi of yt square dy. Why I am putting it is just not restricted to one axis. Suppose I want to find the probability of finding the particle along the y-axis. So, I write P of y dy will be equal to psi of yt square dy. Now, the total probability is 1. And if you have to force the normalization condition, again you will write integral minus infinity to infinity P of y dy. So, this is equal to integral minus infinity to infinity psi of yt square dy is equal to 1, or what we have seen along the x-axis is psi star, which is a function of xt, is equal to 1. So, we are going to apply this normalization condition. Now, what we are going to conclude here is, in classical mechanics, when energy of the particle is less than the barrier height, particle must be reflected back. Means, I told you what is a barrier. I am keeping it enclosed in a box. The particle is there, and the energy of this particle is very less. It cannot cross this barrier and go out. So, once it comes here, it should be reflected back. In quantum mechanics, what we are seeing? The de Broglie waves corresponding to the particle are partly reflected and partly transmitted. So, So some of the energy is transmitted also, we are seeing when it is coming and hitting the boundary. So what we are understanding here in quantum mechanics, so this is a very important point which we have to consider. But what happens if the barrier is infinitely thick? If the barrier is infinitely thick, then what happens? Then the transmission probability will be zero. It will again be reflected. So what we are trying to do here is connect from classical to quantum. So in classical mechanics, if the barrier height is very high and the energy is very less, the particle will be reflected. In quantum mechanics, we consider that partly reflected and partly transmitted. But if the barrier is thick, then there is no transmission. Then the probability of transmission is zero. So then it has to be reflected back. Now, if it has finite thickness, if it is not infinite, if it is finite, then there will be a finite probability for transmission. And however small, the particle will tunnel through the region and emerge in the region. So if it is able to transmit, it will come out. But the particle does not go over to the top of the barrier, but it tunnels through the barrier. Are you able to understand? So what we have can conclude is, higher the barrier and wider the barrier, less will be the chance of the probability to for the particle to get through the barrier. So if the height of the barrier is more and the width is also more, then the chance for the particle to get through the barrier will be less. Now to conclude, there are several advantages to understand this wave function. Although sometimes it looks complex, but there are many advantages of understanding this wave function as representing the elements of an abstract vector space. So whenever you will have to represent the elements in vector space, you use this. And also all the powerful tools of linear algebra can be used to manipulate and understand the wave function. So this is the greatest advantage we have in using this wave function. Now we will try to apply it to a one-dimensional potential box. So what is the probability of finding this along with x? So we have the formula for the function as psi of x is equal to a sine n pi by L into x. Okay. Now we have seen that the probability is always given by psi square of dx. That is what we have, because this is not an observable quantity. If we have to find the probability, we always have to talk in terms of psi square dx. Psi square is not nothing but psi star. So how do I write the value of psi square? So a square sine square n pi by L into x. And we know that we have already derived from Max-Born approximation, this value of a is under root 2 by L. So how do I write the probability now? P is equal to under root 2 by L whole square sine square n pi by L into x. So if I take out the square root and square, so we get 2 by L into sine square n pi by L into x. Now what is the probability of finding it? What they are asking here, we will apply the condition. What is the condition? The potential box of width L. Okay. It is known to be in the first excited state. So here also you need to understand, whenever we take ground state, for ground state, n is equal to 1. Then for the first excited state, we take n is equal to 2 and determine the probability of finding it exactly at the central half. Central half means I take L by 2 because the total width is L. So at the center means x is equal to L by 2. So I will put those conditions here. So this will be 2 by L sine square two pi L by 2 by L. So this gives the value of, you can write sine square in terms of cos x, and the value of 2 pi for cos is 0. So here 2 by L into 0 is 0. So what it helps us to understand, the probability of finding this particle in the first excited state at the center is 0, means we will not find the particle at that position. So because I told you, if you know the wave function and you are talking in terms of probability, so that you can locate the exact position of the particle. How you are able to locate is using the formula. I hope with this example, the concept of the wave function is very clear to you. Here I'll end the session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.